Welcome to today's episode, where we're diving into the intriguing world of database transactions. We'll explore how these transactions are managed and recovered, uncovering the essential principles that keep our data both reliable and intact, especially when things go awry. Along the way, we'll also touch on some optimization techniques that can really boost data retrieval, focusing particularly on B-trees and caching strategies. So let's jump right in. At the core of any database system is the concept of transactions. Think of a transaction as a single, indivisible unit of work. To keep things running smoothly, these transactions adhere to what we call the ACID principles: atomicity, consistency, isolation, and durability. Essentially, each transaction must either be fully executed or completely rolled back. This strict adherence is vital for maintaining data integrity, particularly in environments where multiple users might be interacting with the database at the same time. Now, let's talk about transaction management. A solid transaction management system is crucial for making sure transactions are executed properly. This is where the transaction manager comes into play. It coordinates everything, ensuring that all operations within a transaction happen in the correct order. The transaction manager initiates transactions, keeps track of their progress, and decides whether to commit the changes or roll them back based on their success or failure. But the transaction manager isn't working alone. There's also the lock manager, which plays a key role in preventing conflicting access to data. It does this by implementing locks that control how transactions interact with the database. By managing these locks effectively, the system can avoid issues like deadlocks, allowing transactions to run smoothly without any interference. To enhance data access, we have the page cache, which acts as a crucial link between persistent storage and memory. This cache stores frequently accessed pages, enabling quicker retrieval and cutting down on those time-consuming disk I/O operations. Not only does the page cache boost performance, but it also keeps track of the states of these cached pages, ensuring that the most relevant data is always available for transactions. Another important piece of the puzzle is the log manager. This component tracks all the changes made to cached pages and is essential for recovery processes in the event of a system crash. By maintaining a detailed log of all changes, the log manager helps the database restore itself to the last known good configuration, minimizing data loss. Understanding how the log manager interacts with other components is key to ensuring the resilience of our database systems. As we dig deeper, we face challenges related to memory and disk I/O management. Efficiently managing these resources is vital for maintaining optimal performance. This is where techniques like page pinning come in handy. Page pinning allows frequently accessed pages to stay in memory, reducing the need to access the disk. This strategy not only enhances performance, but also helps the system handle high workloads without sacrificing speed. Now, let's shift our focus to optimization techniques, particularly B-trees. These are widely used data structures that help organize and retrieve data in databases. To improve data retrieval performance with B-trees, we can implement advanced caching strategies. Since the higher-level nodes in a B-tree are accessed more frequently, pinning these pages in memory can significantly boost efficiency. By keeping the most accessed parts of the tree readily available, we can minimize the need for disk access during queries. This approach allows the database to prioritize retrieving data from the lower levels of the tree that aren't cached, resulting in faster query responses. By optimizing how we cache B-trees, we can effectively reduce the overall load on the system, leading to a better user experience. As we wrap up this episode, we've unraveled the complexities of database transactions and their management, emphasizing the importance of ACID principles in maintaining data integrity. We've explored the roles of various managers within a database system, including the transaction manager, lock manager, and log manager, all of which contribute to the reliability and resilience of the system. We've also discussed optimization techniques for data retrieval, particularly focusing on B-trees and caching strategies. By implementing these techniques, we can enhance performance and ensure that databases operate efficiently, even under heavy loads. Thank you for joining us today as we explored these vital concepts in database management. We hope you found valuable insights that will deepen your understanding of database systems. Be sure to tune in for our next episode, where we'll continue to navigate through more advanced topics in the world of data management.